Okay, this is chapter 2, the nature of molecules and the properties of water. If you've had some chemistry in the past, then you may find this chapter a little bit easier. If not, I do plan on taking it each section at a time to break it up. So some of you may want to take it a section at a time and make sure you have enough time to process each part. Some of you may zoom through the whole thing. So it just depends on your previous work, and my goal would be to get us all by the end of the chapter kind of at a certain level so that we can go on to chapter 3. So there are certain fundamentals that I have to present and teach you and for you to learn. So you've already done the preview activity. I'm going to start with section 2.1. All matter is composed of atoms. So the atom, you'll remember from the biological hierarchy that we studied in chapter 1, was the first item on our hierarchy. And it is the unit of matter, not the unit of life. The unit of life is defined as the cell, but the matter is composed of atoms. Atoms are composed of subatomic particles. Subatomic means smaller than the atom. And the subatomic particles that we're going to discuss are called protons, neutrons, and electrons. It turns out that there are particles even smaller than these, and I am not going to delve into those particles, nor am I really qualified to do so. So that would be a different course. So we're going to look just at protons, neutrons, and electrons. You have to know that protons are positively charged particles. Neutrons are neutral or uncharged particles, and electrons are negatively charged. So one proton has what we call a 1 plus or plus 1 charge. An electron has a minus 1 charge, and a neutron has no charge. In addition, the location in an atom, in a typical atom, the protons are located in the nucleus. Unfortunately, the word nucleus is used at the atom level of the hierarchy of biology, and we'll use the word nucleus in this chapter. We're talking about the nucleus of the atom. The same word is used at the cell level of our hierarchy, but it refers to something different, but it's also called the nucleus. So in this context, nucleus refers to the middle of the atom. Later on, we'll use the same word, but it will refer to something in the cell. So unfortunately, the same word is used in both cases. But the nucleus of the atom is the center, considered the center of the atom, and that's where the protons are. Also located in the nucleus are the neutrons. And then moving around or outside of the nucleus, but still considered part of the atom, are the electrons. So sometimes we call that the electron cloud that surrounds. It's where the electrons, and the electrons move constantly, but they are in a sort of a zone, a defined zone around the nucleus, but not considered in the nucleus. One other thing I would add is that protons have a mass, a weight of 1 Dalton each. Neutrons have a mass of 1 Dalton each. And electrons are considered to have a negligible mass. Negligible means small. There is a mass, but it's so small that we tend to not count it in the overall mass of an atom. So this shows you the atomic structure that I was trying to describe with my hands. If you have a hydrogen atom in this first column, you would have hydrogen always has 1 proton and 1 electron and no neutrons. So given that information, you can tell that the proton weighs a mass of 1. The electron doesn't count in the mass, so the mass of a hydrogen atom is 1 Dalton. And in terms of charge, a proton has a +1 charge, an electron has a -1 charge, so that cancels out, so the atom would have no overall charge. And then they're trying to show you sort of the arrangement or structure of the atom. They're showing you in the center, they're showing you that proton right in the middle, in the nucleus. And then in the first picture, they're showing you kind of the zone where the electron could be, zooming around. In the lower image, they're showing you what's sometimes called the Bohr model of the structure. It's not super accurate, but it gives you a way of thinking about the electron at a distance from the nucleus, but traveling around. But it doesn't actually travel in a flat circle. It travels in more of a general area. So two different ways that artists try to show the structure of an atom, and neither of them quite gets it, but it's good enough for us. In the second column, you have oxygen. Oxygen has 8 protons, 8 neutrons, and 8 electrons. You're not going to have to memorize this. You'll be told how many are in each type of atom. And because oxygen has 8 protons, 8 neutrons, and 8 electrons, what that means is the mass of one atom of oxygen would be, remember, 8 protons. Each proton has a mass of 1 Dalton. And 8 neutrons. Each neutron has a mass of 1 Dalton. And 8 electrons, they have no significant mass. So we would just add the 8 Daltons from the protons and the 8 Daltons from the neutrons, and we would get 16 would be the mass of one oxygen atom. And the charge of one oxygen atom, the way that this has been presented, since there's an equal number of protons, which have a positive charge, and an equal number of electrons, which have a negative charge, the charge of the overall atom would be 0 or neutral. And the neutrons don't contribute any charge to that consideration. All right, so to review, atomic number and atomic mass. If the number of protons equals the number of electrons, then the atom is electrically neutral or charge neutral. The definition of atomic number is the number of protons in an atom of an element. So for hydrogen, the atomic number is 1 because hydrogen always has 1 proton in each atom. The atomic number, the number of protons, is the identity of the element. So if you had hydrogen, which has 1 proton, and then somehow you were able to add another proton to that nucleus, it would no longer be hydrogen anymore. Because by changing the number of protons in the nucleus, you are changing the identity of the element. In that case, the element would be, or the atom would be helium. But you don't have to remember that. But if you change the number of protons in an atom, you're changing the identity. And the identity means what type of atom it is. So protons are the identity of the element, the number of protons in the nucleus. And so atomic number, that is the number of protons. So the atomic number of hydrogen is 1. The atomic number, if I go back to this example of oxygen, is 8, because oxygen has 8 protons. And then the atomic mass, I reviewed that already. That's where you add together the protons and the neutrons together, because each proton and each neutron have a mass of 1 Dalton, and the electrons have no significant mass, so we don't add that in. Now, what about electrons? Electrons have a charge, negative, but they don't have any significant mass. If an atom has an equal number of electrons and protons, then we said that that atom would be electrically neutral. But what if there was an atom that had different number of electrons and protons? For example, let's say you had an atom that had 8 protons, but only 7 electrons. It would have one more proton than electron. So 8 protons, 7 electrons. That means it would have an extra positive charge overall, 1 plus overall. If you had an atom that had more electrons than protons, then, for example, if you had an atom that had 9 electrons and 8 protons, then it would have an extra negative charge. So overall, the atom would have a -1 charge. So it's if they're imbalanced, then the charge is based on whatever particle is contained more. So if there's more protons than electrons, there'll be some amount of positive charge overall. If there's more electrons than protons, there'll be more negative charges overall. So we have names for these. Ions are charged atoms. And listen to how I pronounce this word, cation. I know it looks like cation, like a vacation or something, but it's a cation. A cation would be an ion specifically that is a positive charge. And to remember this, sometimes students remember that the T in cation, a T looks like a plus in a way, at least a lowercase t. Or some people like cats, so they think cats are a positive thing in your life. Whatever mental trick you need to remember that. Anion is the next one. An anion, which is a little bit of an unfortunate term there, but all one word, anion is a negatively charged atom. So anion is a negatively charged. And so anion has an extra N, I guess you could say, stands for negative. So you want to remember which one's which. Cation, the positively charged ion, anion, the negatively charged ion. And finally, we have another I word, isotopes. So if you have an atom, let's say that has 8 protons, if you change the number of protons, then you change the identity of that atom. If you change the number of electrons, you change the charge. And if you change the number of neutrons, then you create what we call isotopes. So isotopes are atoms of the same element, which means they would have to have the same number of protons, but they contain different numbers of neutrons. And so what that does is it creates atoms of the same element, but that have different mass, different atomic masses. So the example they've given here is carbon. Carbon always has 6 protons. If you look across on this example, all of these 3 diagrams show 6 protons. But the first one has 6 neutrons, the middle one has 7 neutrons, and the last one has 8 neutrons. So the first one is called carbon-12 because it has a mass of 12 daltons, 6 protons and 6 neutrons, each weighing 1 dalton apiece. The middle one has 13 dalton, has a mass of 13 daltons because it has 1 more neutron. And the third one has 14 daltons in mass. And so what tends to be true, and they're all carbon, so it's not a huge deal, it's just that some are heavier than others. So in of itself, you know, it's just something that has been discovered. Isotopes are pretty standard. So almost, I can't think of any type of atom that, I think all atoms have some different isotopes. Even hydrogen. Hydrogen has some different isotopes. Most hydrogen atoms have 1 proton and 1 electron, but there are some hydrogens that have 1 proton and 2 neutrons, which would give it a mass of 3. So, but those are more rare on Earth. So typically there's an isotope or a form of the atom that's more common, and then these other isotopes that are less common. Again, you're not going to have to memorize what any particular type of atom has. you'll be given this information, and then you will be asked to make a judgment on, are these different isotopes, or are these different ions, or something like that. So don't panic that you have to remember how many protons or electrons or neutrons any particular atom has, but rather if you're given some information, you'll be asked to assess which term applies in each case. And there will be practice problems on the post-quiz. Electron arrangement. So the chemical behavior of any atom, and we're now starting to move into the concept of not just having one atom, but having more than one atom bonded together. So that's the molecule. The way that atoms bond together, or the way that they interact or behave, we call it behavior, the interaction of atoms with each other. The chemical behavior of an atom depends on really the electrons primarily, okay? So remember that the electrons are moving around around this zone, around the nucleus, but not in the nucleus. And what we usually, in this class, we're not going to delve too deeply into the shape of atoms, but in this picture, they give you a very simple introduction to this. The first two electrons that any atom has, if it has two electrons, will be in a zone very close to the nucleus in a kind of a spherical cloud. And we call it an s orbital, or we call it the first energy level. The next group of electrons above and beyond 2, so for any atom that has more than 2, are going to be in another level that's a little more distant from the nucleus. And those zones where the electrons travel aren't strictly spherical. They can be dumbbell shaped. For our purpose, though, we're going to draw them more like the column on the far, this column over here. We're going to draw them like this, but in actuality, the shapes are a little more complicated. But for us, we're going to do this kind of shell diagram. This is how we're going to think about it. So I just want you to know that when you get to chemistry, if you haven't had it already, that don't be surprised when they start giving you shapes within the atoms. But we're going to deal with it in a simplistic way. So we'll deal with it in kind of this very spherical looking way, which is not truly accurate, but it's good enough for us to solve the kinds of problems that we're going to solve. And then in the third level, again, a third level is even further from the nucleus, and it has shapes, but we're going to pretend like it's one big sphere. So in our class, we only have to think about electrons in the first 3 levels. There are more than 3 levels, but we're just starting out. So we're only going to deal with the atoms that have electrons in the first 3 energy levels, and we're only going to depict them in a very simplistic spherical form, not the more realistic shapes. So I hope that's okay. That's usually how beginning classes do it, right? Okay, so that is the first segment, section 2.1. So I'm going to take a break, and if you're ready to go on to the next lecture segment, go ahead. If not, take a break and review your notes or watch this again.